Hey, CS160 students. This is the type of video slash, demo slash lecture that I hope to provide, throughout the term. Um, what I found over the last couple semesters here, last year and a half or so, is that this method seems to work pretty well versus kind of a designated time for an online lecture. So some of you may have started Lab 1 already. Lab 1 is kind of some conceptual things to help refresh some math topics and start to get you into the content that we'll be doing for the term. Remember that CS160 is a combination of computer science topics and programming. This is not just a programming class. And what I find is that I have a group of students that whip through the Python stuff no problem, but they may fall behind in the other material. And then I have students that whip through the science material and they struggle with the Python programming. So I try to provide resources separately so that you can kind of pick and choose what you need to focus on. Lab 1 has a few problems around algorithms and some kind of math concepts. And so I'm going to show you two things in this video. The first is kind of how I think about algorithms, how I define them, and how we go about solving them. And then the second one is a technique that's used primarily in story problems, which we have a few of in this class as well. So let's start here with the example of this algorithm. And algorithms are used for many things. We'll spend a lot of time in algorithms about halfway through the class, but I want to just kind of give you an introduction to that in the first week of the class. And so we're going to talk about this thing called the Fibonacci sequence, famous number sequence that has a lot of interesting properties. But it's simply put, the Fibonacci sequence is a number sequence where each successive number in the sequence is defined as the sum of the previous two. And by definition, the first two numbers are 1 because you have to start from somewhere. So the first number in the sequence is a 1, the second one's a 1. Then the third one is the sum of the previous two, so 1 plus 1 is 2. The next one is the sum of the previous two, so 1 plus 2 equals 3. 5 is 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13. 8 plus 13 is 21, and so on. So this sequence goes up in a non-formulaic way, right? It's not like the previous one is 3 times or 4 times, or but you have to add the previous two together. And you could read a lot about this sequence if you go to Wikipedia, and it talks about like the golden ratio and some other interesting artifacts where the Fibonacci sequence appears in nature. But for now, we're just going to talk about if I wanted to write an algorithm to create this, I basically want to take this 2-sentence version and create something that doesn't have any ambiguity. And so similar to, I think it's problem 2 in the lab, where I write out each step of the algorithm. Let's go through this relatively quickly, and then we'll go through it as an example. So step 1 is I'm going to define two integers. An integer in computer science is a whole number. Might be negative, might be positive, might be 0, but it is a whole number, okay? And so I'm going to define two integers. I'm going to call one second previous, and I'm going to call the other one previous, and I'm going to set them both to the value of 1. And then on step 2, I'm going to define another integer. I'm going to call it position, and I'm going to set it to the value 3. And then I'm going to define one more integer, and I'm going to call it current. And I just haven't given it a value because in the step 4, I'm going to set it equal to the sum of second previous and previous. Now, if we go through what has happened here, is that so through steps 1, 2, 3, and 4 here, I've set current equal to the sum of the second previous and the previous, so it's now equal to 2. That's what's happened through step 4. In the lab problem that has a similar format to this, I think it's either question 2 or question 3. I'm going to want you to do something similar to this on a different algorithm. And this is an illustration of, I think, a good way to do it, where you can kind of keep track of what's happening. I highlight the cells when they change. Step 5 is a check. It says if the value of position is equal to the target value, then let's stop and display the value of current. What is target position value? This is what value I'm looking for. And so I'm going to show you this as an example where I want to find the 6th value in the sequence. So step 5 here, 3 is not equal to 6, which means instead of stopping and displaying, I would just keep going, right? So now in step 6, I set the value of second previous to the value in previous, and I set the value of previous to the value in current, step 7, and then I set the value of position to its current value plus 1. So if I look at what I'm doing there, I'm taking the value here and copying it into there. I'm taking the value there and copying it into there. And then I'm adding 1 to my position value. And then I go back to step 4. So I'm going to go through and I'm going to execute steps 4 through 9 over and over until it's time to time to stop. So now let's go through the next couple steps here. So we're back to step 4, which is right here, where I recompute current to equal the sum of the previous 2, and now I'm at 3. Then I check to see if I'm done. 4 is not 6, so I'm not done. So then I do step 5, step 6, where I copy previous into second previous, and then I copy current into previous. And by now you kind of see a pattern. What I'm doing is I'm keeping the most recent 3 values of the sequence. And so I guess if we look at it from this perspective, if this is the newest value, I think that hopefully is showing up in the camera, right? If this is the newest value, then we basically take this guy and move it over and this guy and move it over, so that when we're ready to compute the newest value, we have the 2 previous values. And the one that used to be the one before, 2 before, is now off because we don't care about it anymore, right? And so so now we increment the value of position to 5, and then we go back to step 4. Okay, So now we go back to step 4, where we compute a new sum, and now 2 plus 3 is equal to 5. Note that this 5 is the position value and the 5 is the value of current. That's just a coincidence. Okay, 5 is not 6, so we're going to again do our previous moves. We're going to move 3 to 2. Oh, there's a typo right there. That should be 3. We're going to move 5 to there. We're going to increment the value of position and go back to step 4. And in step 4, we add our 2 values and we get an 8. 6 is indeed 6, so we know that we can stop here. And we stop here and we have our result of 8. This is an excruciating level of detail here, right? And it's probably more detail than you'll tend to do with your algorithms. But for at least the first few, as we go through this class, it's really important that you think about this with as little ambiguity as possible. And notice that I don't use code here. One of the biggest mistakes students make when they write algorithms is they give me code. You need to write the algorithms in a clear, non-programming language sort of way. All right. When I post this video, I will include this file as well, so you have it and you don't have to rely on, going through the video to see it all, but I'll include this file. There's one other topic that I want to share, and that's talking about what's called the unit factor method. Now, if you've looked at the lab already, you notice that I have a couple story problems in there. I think I have a story problem around sizes of files, or I think in the between the first couple labs, I talk about sizes of podcasts and number of files in memory and things like that. some of you have a good grasp on these story problems, and some of you may not have had enough of the math, or it may have been a while since you've had the math. I just want to reiterate how important it is to be able to convert between units and be able to think about some of these terms in a mathematical way. This is a method to convert between terms called the unit factoring method, or the UF method. And I learned how to do this, I think it was in high school, but I know that some, like my younger son, he learned it in middle school. And so some of you may have learned this a while ago in middle school or high school. Some of you may have learned this more recently in, say, a college algebra class or a pre-algebra class. And some of this may be old hat, right? If you already have a bachelor's degree and you've done a lot of math and so on. So if you've done this and you see it, as soon as you see this first page and you say, oh, I've done this, fine, great. You don't need to follow, obviously. But I've learned that there are a few students that need a refresher on this, or maybe they've never seen it before. And so here's the unit factor method. And let me just make this bigger so we don't get distracted by some of the other stuff. Unit factor method, here's an example. I want to convert 100 miles per hour to how many feet per second, right? So your question might be, how many feet per second is 100 miles per hour? And the way that I describe this is, step one is I state what I need. And so what I'm looking for is I'm looking for the number of feet per second. And so that's what I'm solving for on the right side. So then I start with what I know. So I say the number of feet per second is equal to 100 miles per 1 hour, all right? Because I have 100 miles per hour here. So the left side and the right side are equal, right? Once I get the correct answer of feet, this is correct, right? I just don't know what this is right yet. Okay, step 3 is a series of conversions. And this is where I'll spend the most time here. I'm going to pick a unit of my choice. I could start with miles or I could start with hours. Doesn't matter. And what I want to do is I want to move one step at a time to get closer to the units that are on the left. So in order to get from hours to seconds, I got to go from hours to minutes first. And then I can go from minutes to seconds. And so what I do in this yellow box is I create a ratio where the top divided by the bottom is 1, because I'm going to multiply this 100 miles divided by 1 hour times 1, because I can't change the answer, right? But if I multiply the numerator and the denominator both by the same amount, then I haven't changed the numeric answer. I'm just converting units. So I put on the numerator 1 hour because I want to cancel out hour on the denominator. And so 1 hour is equivalent to 60 minutes. If I had hour on the numerator, then I'd have my 60 on top, right? So the key thing here, again, is to match a unit and then create a new unit where what's in the yellow box is always a 1-to-1 ratio. And now I can cross out the hour unit. Now I'm going to make a quick edit here because it's important that we cross out the unit only, but not the value. Doesn't matter in this case because you're just multiplying by 1 or dividing by 1, but you'll see here in a moment how that's important. Okay, so there's step 3. Now I look at my remaining units. I have miles and I have minutes. So now I have my number of miles per minute when I compute this out. So I'm not done yet. So I'm going to do it again. And now I'm going to convert minutes to seconds. And I'm going to do the exact same thing here. So I put minutes, I do a ratio of how many minutes equal how many seconds, and then I cancel out the minutes unit. Now I'm getting closer because now I have a unit that matches my destination, but I'm still not done yet. And again, as you can see here, I cross out the units, but I keep the 60 here. So stay with me here as we keep going. I got to do this one more time because I got to get rid of mile, right? So mile was here. So if I page back, oops, this should not be crossed out. So now I can cross out mile. by setting 1 mile is equivalent to 5,280 feet. And I mean, this is just a conversion that you have to look up or have memorized. It's a tough one to remember because it's not a really common number, right? Okay, so now I'm at a point where I have the unit feet over the unit seconds, which matches what I want. So now I just have I have some math that I have to do. So now I take my same thing as before. If I page back, you can see I get rid of all the units that I've canceled out. Actually, I should keep second mile. Keep that. Now I have a bunch of math to multiply out. So 100 times 1 times 1 times 5,280 is 5,280,000. And 1 times 60 times 60 times 1 is 3,600. And if I multiply this out, I get an answer of 146.67 feet per second. And there's my answer. Many of you can do this quickly. You just, oh, I need to multiply by 5,280 and divide by 3,600, right? You could do it quickly. When I ask you to show your work on problems like this, doing something like this is awesome, right? Doing something like this generally is good enough to show me your steps. Common mistakes people make is they only multiply or divide by 160, just a single 60, because they go from hours to minutes when they meant to go to hours to seconds, for example. Okay, let me show you one more example as a single page. Say that I want to have you convert 57,600,000 bits per second to kilobytes per hour. And so I do specify here what KB means here. Kilobytes for this, just assume that a kilobyte is 1,000 bytes. And if this is not familiar to you, it will be shortly. I think what I've learned is that most students know what a kilobyte is, and they know what the difference is between a bit and a byte. A couple students may not be, and that's okay. And so I want to go from kilobytes, or I want to get kilobytes per hour. So I write kilobytes an hour on my left. And then again, what do I start with? I have a number of bits per second. And so then I need to go second to minute and minute to hour in the same way I did with the previous example. And now I got to go from bits to kilobytes. So I go from bits to byte. 8 bits, if you're watching my mouse move, equals 1 byte. So I can cancel out that unit. And typically when I do this and I'm writing, I'll cross things out as I'm doing it, right? So I'll write 8 bits and I'll cross out bits and 1 byte and so on. And then 1 byte or 1,000 bytes to 1 kilobyte. And then I come up with, if I multiply the numerator and the denominator, generally you can do a lot of this without a calculator, and you could start to simplify and do things kind of at once. And if you notice here, if I have a bunch of zeros on both the numerator and the denominator, I can eliminate the same number of zeros. And that makes my math a lot easier. And you might recognize it from this larger fraction, and you might recognize it from here, but this just happens to be equal to 2 kilobytes per hour. And so it's always okay to eliminate the same number of zeros from both the numerator and the denominator. In fact, you can even do it as you go. Like you can get rid of a 0 there and a 0 there, and then you can get rid of another 0 and so on. You'll learn methods on how to do this as you get more versed and get more practice doing this. For those of you that have bared through this whole video, thanks, and hopefully it helps you. If it's new information to you, we'll use this a fair amount in this class, especially in some of these early labs. And I guarantee that if you take a physics class, let's say that you need a physics class and you've never taken one, you will need to use this method in your physics class, for example, and in some other future math. So as with the other file, I will provide this file with the video so that you have it. And as usual, if you have comments or questions, please post. as well as feedback on how to improve the video for next time. Thanks for watching.